today. We are honored to have a true pioneer in the field of artificial intelligence. Our keynote speaker is Professor Lissy Kurian John, is a Trueshead Foundation Chair in Engineering at the University of Texas at Austin. Dr. Lissy Kurian is an accomplished individual with over 30 years of teaching experience in the area of architecture, computer systems, embedded systems, integrated circuits and systems, software engineering and systems. Her groundbreaking work on method and apparatus for increasing task execution method has earned international recognition and significantly contributed to the advancements we see today. Dr. Lissy Kurian received her bachelor's degree in electronics and communication from Engineering College of Engineering, Trivandrum, master's in computer engineering from the University of Texas, and PhD in computer engineering from the Pennsylvania State University. She is a recipient of many awards, including National Science Foundation Career Award, University of Texas Austin Engineering Foundation Faculty Award, Brown and Root Engineering Foundation Young Faculty Award, University of Texas Alumni Association Teaching Award, Pennsylvania State University Outstanding Engineering Alumnus Award, and George A. King Professional Engineering Achievement Award. Professor Lissy Kurian is the editor-in-chief of several reputed international journals, including IEEE Micro, and has served in the editorial board of IEEE Transactions on Computers, ACM Transactions on Architecture and Code Optimization, IEEE Computer Architecture Lectures, IEEE Transactions on Sustainable Computing, and IEEE Transactions on VLSI. She has authored several books and more than 300 research papers. She holds 20 US patents, and she's a fellow of IEEE, a class of 2009, and fellow of Association of Computing Machinery, and fellow of American Association for the Advancement of Science, and also fellow of National Academy of Inventors. Today, Dr. Lissy Kurian is going to share us how we can leverage the potential of machine learning responsibly and effectively. I'm confident that her talk will be thought-provoking, insightful, and valuable learning opportunity for all of us. On behalf of Amal Jyoti family and all those who are assembled here, I extend a hearty welcome to you, Dr. Lissy Kurian John, ma'am. Please join with me to give a big applause and welcoming her. I extend a cordial welcome to our revered director, Reverend Dr. Roy Parambil, our beloved principal, Dr. Lilikuti Jacob, our respected deans, heads and faculty colleagues. And I'm happy to say that the beloved husband of our chief guest, Professor Dr. Eugene Brito John, is also with us very much. Sir is also a professor in University of Texas at another place. So cordially, I welcome you to sir this platform. My dear students, you are the true beneficiaries of this session. Your presence and enthusiasm for the field of machine learning are truly inspiring. I welcome all of you to attend the session effectively and interact with our eminent speaker, Dr. Lissy Kurian John. Thank you all. Thank you.
Good morning. It is a pleasure to be here. I have come up to Kanjirapalli a few times when I was in high school or pre-degree time, but after that I have never come here. So it is definitely a pleasure to be here. And thanks for all the generous introduction, and happy to meet all of you. I'm going to talk about machine learning, focused more on machine learning and its effect, or how system design has been influenced by machine learning and so on. But before I go into the talk, I would like to say thanks to the Kerala Catholic Church, which gave me my education up to 12th grade, and the formation that was helpful in my upbringing. So the KCSL, the Kerala Catholic Students League, I was very active and greatly helped me to shape up. And one of the people who was very instrumental in that was Father George Kolath, who passed away about 20 years ago. But he was the first KCSL director in Kanjirapalli when Kanjirapalli diocese was formed. And earlier, I came to Kanjirapalli mainly for some KCSL camps in Kanjirapalli, and Father George Kolath was the director at that time, and that's how I happened to come here. So KCSL was very instrumental in shaping me, and I would also say the very first time I met your Madam Principal was at a KCSL competition. I believe it was an essay competition. Probably I was in 8th grade or 9th grade, something like that. So when you get opportunities to be active in our student organizations, make use of it. It really helps to develop you. And when I was coming here, the first thing I looked is, I need a picture of Father George Kolath. So I just went on Google and looked for it. And the place I saw the picture was in Minnesota, where he was a priest for some time. And I would say his legacy still continues because this young person received an award, the Father George Kolath Award, among 10 other people. And I thought Father Kolath touched many young people when he was in Kerala, but he also touched a lot of young people and continues to touch young people's lives even now. I would also like to give thanks to the University of Texas, where I have had opportunity to do research and teach, and also have wonderful colleagues like the ones on the screen. Dr. John Goodenough, he is 2019 Nobel Prize winner in chemistry. He was one of my colleagues. And he was a very nice person and a firm believer in Christ as well. And another person an esteemed colleague is Dr. Bob Metcalf on the picture in the bottom right. He is the winner of the Turing Award, which is like the Nobel Prize in computer science. And both have been my colleagues, and the University of Texas has given me immense opportunities to do research and have wonderful colleagues like that. I also want to give thanks to my students. These are my current PhD students on the left side in that picture. I have graduated about 35 PhD students, and I have about 10 of the students right now. Many of them are from India, some have been from China and other countries in the world. So, going into the topic, machine learning meets hardware design or system design. So, machine learning and AI has emerged out to be a very powerful force during the last 10 years. It has influenced almost every field in the world, every domain, medicine, pharmacy, material science. You talk about any field. They are either helping to make machine learning better, or they are using machine learning to make their fields better. Either way, every field is meeting machine learning now, either contributing to the field or benefiting from machine learning. And I have been a hardware designer all my life. And hardware design, system design, again, it's the same story. It has met machine learning, and we are making hardware for machine learning. We are also using machine learning and AI to design hardware faster and more efficiently. So my talk will have two parts. One, how you make systems and hardware for machine learning, and the other, how do you use machine learning to make hardware? So the general problem in the field is machine learning. I'm sure you are all excited with using ChatGPT or other generative AI tools, They are pretty impressive. But the machine learning models behind these tools, they are getting larger and larger every day. In ChatGPT, there are 175 billion is 10 to the power 9, parameters or weights. That what it means is, when you present any input, the input is actually multiplied with 174 billion parameters to compute the answer. So to predict the next word that it is going to tell you, it is doing billions or trillions of multiplications and additions. It does it very fast, so you don't realize that it is doing that much work, but it is doing a lot of work. The work is done parallelly on many computers at the same time, so it goes very fast. So what kind of hardware do you have to design in order to do things like that is a problem and an important research issue for many companies as well as researchers. So ChatGPT at this time is pretty small compared to some of the newer models that are coming, which have trillions of parameters. In this picture, ChatGPT is at the very first set of blue dots. So it's somewhere in the middle, and you can see that the new models are a lot bigger than ChatGPT. Training these models to the level it is useful takes a lot of work. OpenAI, the company who made ChatGPT, they used 285,000 CPUs, 10,000 GPUs. You might have heard of NVIDIA and the company that makes these graphics processors called GPUs. 10,000 GPUs, 285,000 microprocessors or CPUs, and 400 gigabits per second of network in order to train ChatGPT. GPT-3 took 26 days to train with 10,000 GPUs, and GPT-4 takes 5 to 6 months to train even when you use 10,000 GPUs. So when you use ChatGPT, things happen fast, but the training itself took several months with lot of resources. All these resources consume energy. It is a lot of energy that is used to train. And every time you do inference, you don't use this much of time or resources, but it is a lot of computations that is happening. And every country is trying to make their own generative AI model, so a lot of models have to be trained, lot of resources are used in order to train the model. One of the sad things is the energy efficiency of AI is significantly inferior to the energy efficiency of the human brain. The human brain spends about 20 watts in order to be functioning. These AI hardware engines are of course using lot more, several times more watts in order to compute whatever it's computing. In 2017, the Turing Award winners, when they gave their lecture, they put a number out there saying the energy efficiency of the human brain is 500,000 times worse than the energy efficiency of AI is 500,000 times worse than the human brain. So the human brain, as I said, it takes only 20 watts. So these ML models getting larger and is a big problem. They take a lot of energy, and these two problems are difficult for whether AI is on the cloud or AI is in embedded devices in your phones or AI is in medical sensing devices attached to your body. All of them, this energy is a problem. On the smaller side, if you have an embedded device on your body, we don't want it to be heating. We don't want it to be taking a lot of battery that it dies very fast and you have to replace it too soon. And on the cloud, Many of the data centers are taking more electricity than steel plants. The data centers are taking more electricity than entire towns and cities. It is a lot of electricity that is consumed. So reducing the energy consumption of AI is an active area of research, not only in universities, but in companies. And many companies are investing in power plants because they want power to be available to do AI in the future. So reducing energy consumption is an important topic of research in the world. In that front, how to reduce energy, of course there are, the computer architecture or the system will be reshaped to take less energy. But there is also research happening in many fields like material science to find new types of materials, so the current transistors may not be the best for future. So if you can invent some new types of materials and new types of computing like quantum computing or new types of things. So AI has brought together all kinds of fields of science and engineering because there are opportunities for everybody in order to support designing systems and infrastructure for AI. Even for power systems, power distribution, everybody thought we knew how to generate power and distribute power. We have been doing it for factories and all kinds of industrial establishments. But the arrival of AI has brought new problems that there is so much more research happening in how to create a stable power grid. So every field, including chemistry, physics, material science, many branches of engineering, they are all working together to support AI and also using AI. AI is helpful for them. When it comes to accelerating hardware or making hardware for AI, there are 4 common approaches. The one on the left side is a CPU or the common microprocessor. Everybody knows how to program it. You can write a program in C or Python and you can run it on a CPU. It's very flexible. Second from the left is GPU or the graphics processing unit. The graphics processing unit, NVIDIA is a company that makes it's very popular. Their graphics processing units are very popular. AMD also makes GPUs. So these kinds of processors, not as flexible or friendly as the CPU, but they are fairly general purpose and you can program them with Python, CUDA, some languages like that, and they're fairly easily usable. But on the right side, rightmost side, is a custom chip. A custom chip made just for the application, in this case AI. It's much more energy efficient because it's only doing AI, and we can optimize it to just do AI. So the right side chip is very efficient. The left side chip is very easy to use. The left side chip is flexible. If instead of AI you want to run something on it, you can run it on the left side. On the right side, you will make a special chip for each application. So if you want efficiency, including energy efficiency, you can go to the right. But then, making a chip is not a quick thing. You design a chip, it might take 6 months, 1 year, 2 years in order to design the chip. Even after you design, now in the world, 90% of chips are fabricated in Taiwan. You have to send your design there, they make it, they send the chip back to you. It takes a lot of time. If there are any mistakes in the chip, you have to redo the thing. It takes another 6 months to send the corrected design, get the chip back. So the right side is not very flexible. It doesn't move very fast, but the left side is very flexible and it is easy to do things with it. In all of these, our objective is to get lot of performance, very high throughput, low energy, low latency or high speed. very quick answers. If you type your question to ChatGPT, you want the answer very quick. Low power consumption. So I'll talk about a few things on how to design hardware for machine learning. And some of the topics I would touch are machine learning, believe it or not, when you look at the application and how to make good hardware, 90% of what happens inside the application is matrix multiplication. You would think, oh, I don't have to multiply matrices. What's the big deal in multiplying matrices? These matrices are huge, and so we'll talk a little bit about the challenges there and how companies are dealing with it. We will also talk about how machine learning is used to design better hardware. So, neural networks are basically what is used for these machine learning models. And so, whether it be, there are different kinds of networks, MLP or multi-layer perceptrons, or transformer models and generative AI models. All of them, when you look at the structure, it's full of matrix multiplication. For instance, so I say all roads lead to GEM. GEM means general matrix multiplication. This is the amount of multiplication in ChatGPT. So and the many layers are shown there. I am not expecting you to read all the numbers, but if you look to the right side column, that's the total number of multiplications in that layer. And you can see many of the numbers are 10 to the power 12. That's a trillion. You know, if you add all the multiplications, it's a lot of multiplications. The current models are 1,000 times bigger than that. This was the first ChatGPT, the GPT 3.5. So, general matrix multiplication is the thing that's done in these models, no matter what the model, you know, which country's model or which company's model it is. And how is the industry dealing with matrix multiplication? NVIDIA made something called tensor cores in order to deal with matrix multiplication. A tensor just means a matrix or a vector, maybe three, different dimensions, but it is a bigger, glorified name for a matrix. Google, to deal with matrix multiplication, they made what is called the TPU, or the Tensor Processing Unit. What NVIDIA does is, it has made hardware, all of those gray boxes in the center, they are multipliers and adders to multiply two matrices. One matrix is A, another one is B. The matrices are fed from the sides. The multiplication is done. The answer matrix comes down at the bottom. They can also add it to a matrix already exists. So matrices can be multiplied and added to an existing matrix all with one instruction. 30 years ago, processors did one multiplication. That was the most it could do. 35 years ago, processors couldn't even do one multiplication. They went to a coprocessor to do one multiplication and took the result, and then the main processor computed. So this is a major feat. It is a lot of multiplications that are done in parallel. And I don't want to go into details, but I would just say that they are adding more options of what size data, 32-bit data, 16-bit data, 8-bit data, 4-bit data, such matrices can be multiplied. And Google uses tensor processing units. And what is in tensor processing units is something called systolic arrays. A systolic array is an array where you are computing and feeding the result to the next element in the array, and it goes around, and it is a way to reduce energy because you don't communicate with memory for every computation. And there also you have an array of processors. The matrices are kept on the side, very positioned, and then you just start the computation and a big pipeline and the computation happens. And the result propagates and it comes out, and when it starts coming out, it can come out, new results come out every second, every cycle. And Google is optimizing the size of the matrices it is multiplying, and in every generation, now the TPUs are in the 7th generation. They come up with new things, but fundamentally everything is a matrix multiplier. And you could, with our objectives of achieving high performance, low power, etc., I talked about two different approaches to multiply matrices, NVIDIA's and Google's, and I'm going to present a third one, which is not necessarily an architectural improvement, but it is a technology improvement, which is a wafer scale engine. What it means is, usually, chips are, you have a semiconductor wafer, you make lots of chips, you cut them and have small chips, you put them into a system. This company called Cerebras, they made a chip which is the size of a wafer, which is like a sheet of paper, that big. It's not like small chip, but the size of a paper, sheet of paper. All these chips are interconnected right within the wafer, and it is a different way of building systems, and AI is the one that made it possible to have a useful system at wafer scale. The idea was there 35 years ago, but there was no way to make it. There was no big application which needed it, and all of a sudden AI has given the reason, and Cerebras is a company. No one else is doing it. It is a very extremist view of how to make a big system, but Cerebras is making it, and it is a remarkable achievement also. Made possible because of AI, otherwise they wouldn't have built it. People are also connecting chips in what are called 2.5D chips and 3D chips. You would think every chip is 3D in some sense, but inside you put one chip, you put another chip, you integrate it in 3D, and so chips can be packaged, integrated in 2.5D means you put chips and connect them on using a special thing called a silicon interposer. But 3D is another thing. So the interconnection happens like that. You make these little chiplets and stack them on top and interconnect. And you would think, yeah, okay, what's the big deal? I thought it was possible already. The amount of connections you can do when it is done inside a package is a lot more than when you do it outside. It makes it possible to communicate faster and spending less energy. The main benefits claimed by Cerebras is communication and less energy in communication. There are also processing in memory architectures. Traditionally in computers, current set of computers, we put data in the memory, we put the program in the memory, we fetch the program to the processor, we fetch the data to the processor, you compute in the processor. Moving data 10 millimeters from one chip to another chip takes more energy than doing a 32-bit floating point multiplication. So moving data is very energy expensive, and so reducing the data movement is an important area of research. And processing in memory architecture means you are trying to process or compute right at the memory. On every bit of data, there is some small processing element added on every column of data. So these are all approaches to do AI computing. One approach in the middle is called FPGAs, or field programmable gate arrays. It is not already a processor, it's not already a custom chip. It is in the middle. It is like you buy a fabric and stitch it into your shirt or your skirt or whatever. You can stitch it as many times, open it up, stitch it again into whatever you need. It's a field reconfigurable again and again. That's another approach to make AI hardware. So, some of the research happening is in actually making CPUs, GPUs, FPGAs, all very specific to machine learning applications. So, in this chip, which one of my PhD students made, the red columns that you see are special blocks that were added for AI and machine learning. basically doing some matrix multiplication in an interesting way. And it improves performance. I'm not going into the results specifically, but in order to improve performance and reduce energy. Similarly, another approach is to put processing in memory inside an FPGA. I will also say, the details are not important here, but basically you can improve performance, and all of this is about matrix multiplications, but matrix multiplication is highly sensitive to how exactly you break this huge matrices into small matrices and how you compute. The amount of variability in performance, if you just wrote a Python program to multiply two matrices versus if you used Intel's optimized library, the first option took 21,000 seconds and the last option takes 0.4 seconds. So how different is that? So unless you program the right way, the hardware is not used efficiently. And if you use 21,000 seconds to multiply, this is the same matrix, a 4,000 by 4,000 matrices, to 4,000 by 4,000 matrices, the performance is 63 times different, 63,000 times different. So it's important to program correctly, and that's very difficult for ordinary users. So companies make specific libraries that you can call and do things efficiently. So it's important to use those. And even now, with GPUs, the variability is slightly less, but a lot of variability. These are results from some experiments that show a lot of variability. How do people program these? You have some matrix you want in your generative AI application or ChatGPT. You have to break it down. There are instructions for small matrices. You have to use the right ones. Otherwise, performance and energy will be really bad. About 30 years ago, matrix multiplication was considered not a good benchmark, and 89, Spec is a company that makes benchmarks for benchmarking computers, and they said we are removing matrix multiplication from our suite of benchmarks. They cannot do it anymore. So there is variability even if you do matrices in an FPGA. It's all about how the software will use the hardware. So programming in an optimized way becomes extremely important. In order to do that, you need to understand the hardware, otherwise you wouldn't program it matching to the software. It's all about mapping the applications to the hardware. It's all about mapping the applications to the hardware at the level at which the hardware will support AI. And it is probably in the near future, there will be quantum computers, there will be new materials. Understanding what type of material or what type of computer it is and programming to the level of that will be important, otherwise you don't get good performance. Even power systems are now undergoing tremendous challenges with all the AI applications. Usually power systems, even historically big factories came at 8 a.m. or 9 a.m. maybe the factories start and then the consumption is stable. AI data centers, when they are computing, they take a lot of power. Then computation, they have no data. They have to go get the data from memory. There is no consumption. So power is swinging from full power to about 10% of the power a few seconds at second granularity. That's very difficult for the power grid to handle. So they are working on things like that. So the reason is the computers that are built, we have lots of parallel units which all go into multiplication at exactly the same time, which is a problem for the power grid. If we have 1 million multipliers multiplying at the same time, all of them are done, no one is multiplying, everybody is fetching the next data, it is a big problem. So there is a lot of research happening on things like that. So I have talked a few things about designing systems. Now, how to use AI and make better systems. People are discovering new materials using AI. In olden days, chemistry research or material science research, you would actually, experiments are done by humans, you look at numbers, how are things, you decide, oh, this material has this property. Now AI can do it for you, or AI can basically help you design the experiment, do a lot of experiments and come up with suggestions for new materials. Hardware and systems are the same way. We can use AI to make better hardware. When you design hardware, before you build it, it is important to estimate the performance and power of the hardware you will be building next year. We want models for it. AI can be used to make models for it. Chips contain a lot of transistors. Nowadays, billions of transistors that are interconnected. 35 years ago, people would draw with hand. Draftsmen were drawing lines how to interconnect the chips. It's not done manually anymore. You can use, it was being done with computer-aided tools for 30 years. Now it's even, AI can do better routing, AI can do better placement in order to make chips smaller and the paths be less. AI is very good at that. So AI is being used to make better chips. May have heard these words, low code or no code. AI is writing programs. You can ask ChatGPT to write code. You can ask, there are several programs like that which can write programs. You still need to learn how to do programs because the programs AI will do maybe 95, 90%, in some cases 50, 60%. It can be a starting point, but you have to do the rest. So there is no excuse not to study programming. Just learning it from a coding AI program is not enough. But AI can be used to estimate the performance of future systems. And there is research going on how to use the current computer to estimate the performance of a future computer. And some of these techniques, it's important not to estimate the performance like at minutes or the entire program, but as time is going on, because we need to know the power swings, etc., AI is very helpful for that. AI is also good in, AI techniques are reducing the error in models. The line at the black line, at the diagonal way, that's the zero error point, and AI techniques are reducing the error in those models. The yellow line, the yellow bar shows the error in a before AI model. The green bars are showing with application of AI, these power and performance models are more accurate. They are not just accurate over the whole program, they are accurate at the various phases. When power goes up and down, the model tells that. So it is very useful. But there is also a lot of concern about AI and how big these systems are. In 2024 April, IEEE Spectrum, the magazine, had an article saying, we are looking at about 550 million active lines of code in order to open a garage door. So when you use robotic or automated things, you are using a lot more resources. This task doesn't need any, it's a switch you are flipping on. That's all you are doing. If you can write an efficient program, but if you want to connect and open your garage door from anywhere remotely through your phone, and this application has work on Amazon system and Google system and Facebook system and all of those, then it needs a lot of interface. And you are looking, and this is not an exaggeration, it is true that something that needs just a switch to be opened or closed takes 50 million lines of code. That means cheaper ways to store programs, cheaper ways to execute programs, cheaper and less power consuming ways to store new types of memory, new types of materials, and new types of memory systems, all are important in the future in order to handle things like this. So, if there is so much performance variability, 63,000 words, if I did a small mistake in how I am coding, it will be nice to have AI tell me that when I am coding, hey, this is really lousy, you should look for a better way to program. So maybe, when you are using map applications, it tells, oh, this is the fastest route or something to get somewhere. AI should tell programmers, oh, this is pretty good program, you are doing a good job, or this is really lousy, you may want to improve how it is coded. Lots of different types of hardware. AI should probably tell me where should I run this. And data centers want to know that so they can run some specific application on a specific type of hardware. So in summary, AI and machine learning has influenced every domain of our lives, and we can benefit from AI. We can also try to make AI more efficient and lower power and lower energy. I would say to all the young students in this room, future is bright. AI, while there may be some concern, AI is going to replace all our jobs by the time we graduate, there is another way to look at it. There is so much more you can do when you also use AI, and all the AI that the future the world is going to run needs bigger systems, more hardware. You can build hardware, you can write the programs. With AI's help, you can write better programs. So there is a lot you can do. And I would say there is something in it for everyone here. It doesn't matter what your field of engineering is. You can use AI and you can help AI, and together there is more you can accomplish. For instance, medical sensing devices for continuous monitoring of your health. It is something that can help humans a lot. There is a lot of research needed to make sensors and AI that can be integrated very near the sensors. AI can be used in many ways, helpful for us, and I would end on that positive note. There is something in it for all of us here, and we can do more things, and AI will enable us to do more things. I'll be happy to take questions.
Thank you, ma'am, for your valuable sessions. Now it's time for the audience to ask questions. We have some time reserved for asking questions. Yeah, Renil.
Good morning, ma'am. Ma'am, at what point did you realize that you wanted to specialize in ML?
At this point, specializing in ML is one thing, and it is also because it's affecting everybody, it's good to know some ML. So everybody will benefit from some machine learning and AI, and specializing in ML, you can specialize for ML algorithms to make these, all of this maybe we are doing in really inefficient ways, and there are much better, efficient methods of AI, and which would be invented by some good algorithmic expert, some good mathematician. So even knowing the math and the AI can improve the AI, but you can also use, so I would say the specialization, first have a broader, include AI in your breadth, and then if you like it so much, and very specialized in AI is either programming or the mathematics behind it. If that looks interesting to you, go in that route. Otherwise, do some AI in your broad base of skills, and then use that AI to do whatever else you are doing. Both are fine.
Thank you, ma'am.
Thank you. We have still ample amount of time so that you can ask questions, whether on this field or how about, yeah.
Ma'am, when we are designing a system using ML, how do we know if it adds more value or more complexity to the system?
Every field, hardware design, has some standard benchmarks. on which what is the performance and what is the power, you can find out what did people who did things before get. So standard performance benchmarking organizations have results on their websites for certain big standard applications. So when you design your new hardware or new software or the new system, you can look, oh, okay, they were doing this many inferences per second. How many inferences per second am I doing? Or I am doing less inferences per second, but the number of the picojoules, the energy per inference, this is what has been happening in the field so far. What I am doing gets this energy per inference. So standard benchmarking can be utilized, and there are benchmarks which are simple enough to be run on small things, and also ChatGPT like big and complicated benchmarks, which it is very difficult for research at the research level to run. But you can run, there are many smaller benchmark programs for detecting digits. For example, there is a very simple one called eminent. It is detecting whether the digit is 0 to 9. So that's like a small one, and then on the larger end there are ChatGPT and other things. And there are many benchmarks in between, and the performance of those benchmarks on standard systems are well known. So you tell, oh, have I improved anything? Have I improved the energy? Have I improved the performance? At least one of the things. And usually when you do research, it's not easy to improve everything. If it is so easy to improve everything, the world would have done it already. So maybe you improve one thing and you improve the energy. You did not improve the absolute throughput. That's okay, because the energy is more relevant for, let us say, a medical sensing device you put on your body. So in your domain, maybe you have made one improvement. That's how to decide, yeah, this is pretty good for this.
Thank you, ma'am. Ma'am, for students who are interested in ML-driven system designing, what all topics or courses we should focus on?
So you should improve your skills in both hardware and software. So on the software side, of course, data structures, algorithms, all of those are basic programming skills in different languages, those are important. On the hardware side, the fundamental one is computer architecture, and then digital design. So computer architecture will teach about various types of processing, philosophies, and so on. Operating systems is very important. Compilers are important because if you compile in different ways, you get totally different performance. It's important to understand that. In general, any new skill in hardware or software is helpful. You will not learn everything you need while you are in college. I can tell that for sure. New things will keep coming. So basically pick up the fundamentals and be willing to learn every day in your life later. So the opportunities, whatever is available to you, use them. And I can say was very impressed with what I saw here with the campus and the system that you have here. Utilize all of the opportunities, take courses which interest you, which are available to you, and be willing to learn later. And every day keep learning what the world is. You will be working in a world which will be changing very fast, and new things will be coming. So the basic thing is to pick up the fundamentals now to get your first job, but be learning every day so you are employable for 30, 40 years.
Thank you, ma'am.
Hello, ma'am. What I need to ask is, how can a student train impactful ML models without the access of large data centers?
It's a tough question because the training models take a lot of resources, and training new models is currently difficult except using data centers. But if you are working on models for near the sensors for medical applications and things like that, everything does not need a model as big as ChatGPT. There are plenty of applications which need small models. So you could be training those on even a laptop with a GPU. You can be training those models. So if you want to work on generative AI and a large thing like ChatGPT, without data center, that'll be hard. But if you are working on small models for everyday life, not language models, but maybe sensing, anomaly detection, there are models which are used for detecting, like in cybersecurity or something, where a network, whatever request is coming is hacking or real. That can be detected with small models. So there are models for many everyday applications which are small enough to be trained on even a laptop.
Thank you, ma'am.
So I wanted to ask a question that if we can run a model in the CPU, most of the models are run in a GPU, but I've heard that models can be run on a CPU. Do you know anything about it?
Yeah, GPU is somewhat necessary for training, but for running a model and doing inference, for many inferences, CPUs are better because CPUs take less power. So CPU models, if you go on this benchmarking company called MLPerf, who are the machine learning benchmarking people, you can see that there are some CPU models that beat the GPU model, especially when you consider energy per inference. So there are CPU models, but training a model in general takes a GPU because the current machine learning models need a lot of training in order to become good. But even there are some new types of models that are emerging which are more lightweight, and those models could be trained on a CPU. So there are models for edge inference. Edge means as opposed to the cloud, this is closer to embedded devices or closer to IoT, small devices. Those models can be sometimes trained on a CPU, but many models can be run on a CPU for lower energy. And the way the GPUs become useful for inference, they usually batch many inferences because a GPU is a massive machine with a lot of parallel processing. If you run one inference on a GPU, it will take a lot of time and it will take a lot of energy. So for small batches of inference, a CPU is actually better than GPU.
Okay, hi. As we know, we are approaching a saturation point in Moore's law. That is, the number of transistors is not doubling. So do you think there is an industry shift happening soon towards quantum computing or any other hardware design?
There has been always this talk on how we are reaching the boundary of something. When two transistors were integrated to make the first IC, Texas Instruments did that. Somebody said, maybe at the most you will integrate 10 transistors. Okay? So, and now there is more fundamental physics limits happening because transistors are coming to angstrom level, or basically they are so tiny you cannot go any more than one atom. So you basically are looking at really small devices, and there is some limit coming from physics. And there are these materials which are nowadays called 2D materials. They are not considered 3D anymore because it is so thin that it is a thin film and it is basically 2D material. So there are some physics limitations coming that way, it might appear. But in the talk, some of the things I said, the 2.5D chips, the 3D chips, those are all ways to overcome some of those limits. 3D devices called monolithic 3D. It's not like I put couple chips and interconnect them, but I have a material in which I am interconnecting inside the chip. those are coming. So although there are limits coming, very innovative engineers are in general pretty innovative people. They keep coming up with new techniques how to deal with, and the packaging, like the 3D packaging and the integration of different types of technologies, a lot of improvements are coming. So I'm very hopeful that although there are these limits that are thrown out there saying we cannot be continuing this trend of putting more together, maybe there are also other innovations coming, and some from material science, some from other types of computing like quantum computing. Right now, quantum computing still has a lot of challenges to overcome, but maybe they will be overcome, and that will still enable more computing.
Good afternoon, ma'am. The very own godfather of AI itself had his own concern about AI having an autonomous mindset and taking control in a sense. It's just a concern. Since we are providing AI with all these hardware and capabilities of designing our very own technologies, do you think it is more reliable in the long term and keep it under human control?
Jeffrey Hinton did express that concern, and he's concerned, he was the father of neural networks, did all this research all these years, and finally he is concerned that AI may overpower humans. So that concern is genuine. The risk that can come with AI is we are a lot less aware of what is happening. If you are manually doing something, you are more aware of it. If you are relying on AI to do it, your own skill to do that is going down. So humans may lose their ability to do a lot of things if we rely on AI for everything. That is genuine concern. I think about it myself. However, it is for humanity probably to decide and come up with good policies, perhaps to limit AI to usages which are appropriate. Will governments react as fast as needed to come with policies? With humans accept it. If you are told, oh, you cannot use your cell phone 24 hours a day, limit it to 1 hour a day, how many of you want to follow with that, right? So limiting usage of something, in general, humans will resist it, and so there is a concern. So appropriate limits and guardrails are to be there. There has been concerns of inappropriate uses of ChatGPT and dangers coming from that. And those who are in favor of technology would say that happened with every new technology. When airplanes came, people died. When any new technology came, things were happening. So there is that pain in the growth of a new technology. But it is true that AI is somewhat above all of those, in that it removes your awareness of what is happening. So it is probably up to us to decide what level of AI do you want to use in your lives. And if we remove awareness from us, like you don't know what's happening, AI tells something and you follow that, there is a risk for humanity. And you may want to read on the 3 laws of Asimov's laws on robotics. And the third law is basically a robot may not overpower its creator. But will extensive use of AI lead to a robot overpowering the creator? You never know. But that's where young people like you, when you go into your jobs, not just in the systems, but also in policies governing use of systems, we probably have to, the government, you have to give enough information so someone can make laws and rules and policies governing use of it. And our willingness to follow such policies is also important, because if we don't do that, our awareness will go down and the robot may overpower us.
So, ma'am, I would like to ask you, how do you see India's native artificial intelligence development in the upcoming 20 years?
It's a very difficult question for me, but I would just say, because one is no one can predict the future. Second is what is anybody's ability, but I would say last year when China made DeepSeek, the equivalent of ChatGPT from China, and they claimed that it takes lot less time and resources to train it. That did, take the world by surprise. Similarly, current AI is so inefficient that there is so much room for improvement. Some smartness in some aspect of the AI may make it 10 times, 100 times, or 1,000 times, or 1,000,000 times better. So, what is anybody's ability to do that? It depends on perseverance, understanding of things, and then trying to be better. And India is pretty good at that. India has a culture that really values education and values perseverance, and with that culture of India, it is quite possible for Indian talent to do that. China did surprise the world. There is a lot of research happening in China and other countries that in US there is a lot of concern that we need to work really hard, otherwise other countries are going to overpower you. India has a chance.
Ma'am, just an additional question about Asimov's law. So, how do you see? So, do you think that three laws are practical in our current sense? Means those were written in the 1950s.
But they are very fundamental. It was also more in the terms of fiction rather than truth at that time.
So I admit I love his stories, especially Foundation and the Earth and Foundation's The Edge.
I quite didn't get that, but I would just say it is fundamental in the sense of if you are not aware of something that you are creating, usually when you make something and the robot and with AI and with machine learning, what it will do under some circumstance is not known to the creator. It is almost like we humans have our own independent mind. The robots are having the independent mind when they are learning by themselves. So what they will do is unknown, and so that is why Asimov's law can be broken there. Because of that ability. Machine learning, you don't explicitly program what to do under certain circumstance. So all you can do is, don't do this. So we can put rules on top of the machine learning system that never do this, never do that, no matter what the AI says. So that's what, guardrails is the name for that. AI is using the word, put guardrails on it. So the robot will never kill someone. The robot will never advise you to kill anyone. The robot will never do certain things which are dangerous for the society. So we do need such rules and guardrails on top of AI, and if that doesn't happen, there is a real danger that Asimov's laws will be broken and AIs can destroy or overpower humanity. It is possible. But hopefully we humans have the sense and the intelligence to limit the use of AI in such circumstances and put enough guardrails that we are still safe from AI.
Hi, good morning, ma'am. Ma'am, my question for you is, during 1960s, we had mainframe computers. So when mainframe computers came into existence, the impact, the better mainframe computers, they gave a huge leaps. Then it just gave very few significant efficiencies. The same were the case for CPUs. Now, keeping human ethics aside, let's keep that aside. My question for you is hardware for AI corporations replacing this? Isn't more like a maintenance and not innovation? And complete shift in NVIDIA's gaming corporations to completely AI and the RAM spike. So isn't more of a maintenance that every few years you have to replace all of these components for just marginal gains?
I quite didn't understand the question completely. Are you saying if NVIDIA designs the hardware using AI?
No, it's more of how in any upgrade to any AI is just efficiency and not marginal gains. It's more about how maintenance and not innovation.
No, innovation is everywhere because 4 years ago we didn't have ChatGPT, right? 4.5, 2021 is when ChatGPT came. The models that are used in ChatGPT, like language processing, natural language processing, in 90s people decided there is no more advancement possible in that. So for 25 years there was nothing in between, and then the development happened like within the last 10 years very quickly. Transformer models and generative AI models came very quickly. No one knew it is possible to predict the next word this correctly using such an approach. And it became possible because in 1996 there was no GPU. There was no way to train models like that. So innovation happens based on what is possible at that situation, which was not possible in the 1990s. So in 1990s, everybody said AI is dead. It is called AI winter. The government stopped supporting AI research because AI failed to deliver. At that time, it was told AI is dead. When I went to graduate school, when I went to US to do my PhD, I wanted to do a PhD in AI. I took my first class in AI, and when you read the book, it is like, I say it is almost like a funeral, it's over. That was the sense of what's in the book. The way the AI was done at that time, programming was done through a language called Lisp, and AI was programmed using rules, and using a rule-based AI system, there was only so much that could be done. So 25 years in between, the world thought AI is not possible. All of a sudden, with GPUs and the large amount of computing, it became truly innovative. The way it's done now is very innovative compared to how it was done 25 years ago. The way it's done is very inefficient right now. That's my complaint personally. So some way to make the efficiency better, energy as well as performance, if it happens, AI may become 1,000,000 times cheaper than how it is done now. That'll be true innovation, and then you can use AI without costing as much money and without costing as much energy. That will be nice. So there is a lot of room for innovation. That's why I would say it will not be incremental. Usually, you move in incremental steps until someone comes up with something truly innovative and really above everything else. Then you start going incrementally for some time, but somebody will come with something that is truly innovative. So I think it's possible. You should be hopeful. You should look for that innovation. You never know. Most innovations come by surprise. It's not planned. You try, you never know when it comes. But unless you keep trying, you will not see it, ever. So you have to be trying to come up with that next innovation. And the day before the innovation, you don't have it. But the day of the innovation, you have it. And there is no guarantee that previous day you are not thinking this will happen tomorrow. So continuous passion towards something and continued perseverance, you will come up with innovations like that.
Can we go back to 1960s for a moment?
Yeah.
Let's imagine we are in 1960s. Now, the mainframe computers, they are just released, and the only upgrades that companies can get are either governments or multi-billion-dollar corporations. Then we got microprocessors, which just collapsed the entire mainframe computers industry. Then CPUs are getting collapsed by cloud computing.
Correct. So the world, IBM had mainframe computers. You had, and the US, the Intellectual Property Office, the one that gives patents, said there is nothing more to be invented. There were people who said at that time, the world needs 5 computers. That's all. The whole world needs 5 computers. And then a bunch of young people from the Silicon Valley, they come up with the concept of the PC, the personal computer that you can have, the Macintosh, the IBM PC. All of those were completely different way of thinking compared to the mainframe. They surprised the world, and they were done with, it's not planned, it just happened because somebody was believing in something other than the mainframe. With the mainframe in those days, you had to rely on, you didn't have control. You just give your code, your punch cards to someone, they run it, they give you the result. And then with the personal computer, so there were some young people who wanted more freedom than that. I don't want to just give this program to somebody, the mainframe, to do it and give it back to me. They invented the personal computer. But you can see a trend the other direction now, because the personal computer becomes difficult to maintain by yourself for big tasks. That's why everyone is relying on the cloud now. Oh, I like to save all my photos on the cloud because wherever I am, I can access it from the cloud. So in some way, the world is coming to, there are 5 big computers. Google has one, Facebook has one, Amazon has one, something like that. That's another way to look at the same old prediction from 1960 and say, after all these PCs where every human has maybe 4 or 5 microprocessors with you or 100 microprocessors in your car, you are coming back to 5 big servers where everything is actually done. So it's very difficult. You can argue both ways, but have to make whatever humanity needs to be done most efficiently with least resources and make it available to the masses. That is a noble task that's not yet solved. Medical monitoring, could you monitor your health and know that something is going to fail and get medical care? Is that monitoring available now? No. Can AI help for that? Yes. Are there new types of hardware to be designed? Yes. Are there new sensors to be made? Yes. Is there new computing to be made? Yes. You don't want to depend on Google's cloud and Amazon's cloud to know the health of your heart. We need local computing to tell me that there is something going to be wrong pretty soon, I better go to the doctor. Is it done yet? No. So there is a lot of stuff to be done. All of you young people have enough problems to solve in this world and make life better. And AI will not do that. AI can help, but you need to do that. So there is enough work, enough innovation to do for all of you to make human life better.
So ma'am, so in the context of modern system design, you taught us that there is a practical difference between designing systems for machine learning versus designing systems with machine learning. So as students, how should we students approach this distinction while working on a real life project?
I would say, it's actually 2 things. They are not opposing each other, they are just helping each other. However, as when you are young, at your age, when you are thinking about where is it that you should be doing something, what opportunities are in front of you, make the best out of whatever opportunity is in front of you. Every opportunity will not, you can't work for every company. You get a job or you get 4 jobs, you pick 1 out of the 4 jobs. And so you have 5 courses, I could pick 1 out of the 5. So there are a few choices in front of you. Take what you like and what you would enjoy. Maybe you don't even know which one will I enjoy. You can talk to other people who have been in multiple of those. But we humans are all very unique people. What interests me is not what will interest you. So different people have different things that we like. And I usually say you should do something you like, because that's when you would put your heart into it and you passionately think about it and have to do better in that field. So if you have an opportunity, you should embrace something that you like. Will that come in front of you? You never know. I would tell a little story. When I was finishing my bachelor's, we had a class in electrical control systems, and that was the thing I wanted to work the least. I wanted to work on microprocessors. It was the fanciest thing at that time. I get a job in VSSC, the Vikram Sarabhai Space Center. I go there. My job was in the control system side. I didn't get a chance to work on microprocessors at that time. I was doing the control system, so pitch and yaw and roll and gimbals and control system. The thing I wanted to work least was what I got to work. Does it, at that time, but that's where I had to put my thinking and do better in that job. So that's what I did at that time. But at the next job, that did open up me to other opportunities where even this experience was helpful in getting the next thing. When I applied for graduate school, so that experience is helpful. So then comes the next set of opportunities. So you never know what opportunity comes. It may not be what you want at each stage, but if you keep working on things, you will get the right opportunity that you really want. And also, sometimes we think we don't like something, but when you start doing it, you may like it more. That's another way to look at it. So being happy with whatever the best opportunity at each time, and trying to make a contribution in that sometimes will open you to really good things which you were not thinking is in that path. So keep taking classes that you like. Among the choices, the best ones. Keep among the choices of jobs you get, take the best one, but stay on it, and I'm sure you will find the thing that you are most passionate about it. And I love hardware design now. I've been doing it for years, and I'm not fed up or tired with it. I love it, even now.
Any more questions? Now we have Director Father Roy with us. I would like to invite Father Roy to be on the stage with us today, and all other respected dignitaries to get into the stage.
I will add one final remark, which is when you get whatever opportunities you are getting in the college, you may take it for granted. You think everyone is getting these kinds of opportunities. That's not really true. What you are coming across is special and unique and good. Make the most use of it. Everyone is not getting the same opportunities anywhere else. So, cherish what you are getting and make the best use of it.
Thank you very much, ma'am, for your insightful words. Now I would like to welcome our principal, Dr. Lily Goody Jacob, ma'am, to address the gathering.
A very good afternoon to you all. Actually, we are very, very fortunate to have such a world-renowned researcher among us today, and for giving us such a enlightening session. Okay, before 3 years back, actually, I had invited her, but she came online for an international conference organized by our EC department. And at that time, and before that also, I had organized an event, International Leadership Summit for Women in Engineering, IEEE. That time also she came online only, but I wanted to bring her to Amal Jyoti So when we planned, we began planning our Silver Jubilee celebration, I had requested her for delivering a distinguished lecture series talk. When she comes to Kerala next time. So months later, when I got a message from her saying that no, I'm coming to Kerala for a short trip, only for 1 week, I can deliver the lecture that time in December. But then I was disappointed because because our holidays, vacation, Christmas vacation was supposed to be scheduled from 20th onwards. But then with the rescheduling of the Christmas holidays, again, I became very happy and then informed her, and she is with us now today. Actually, in 4 days, she came for just 5-6 days. Already she has delivered 3 lectures, one in College of Engineering, Trivandrum, the other one in Marian College, again in Trivandrum, and now this is the 3rd lecture that she is giving us. I know that, you all must agree with me that this is not only a session on this machine learning for hardware design and machine learning with hardware design, but more than that, it is an eye-opening and brainstorming session for all my young students, and so extremely happy about it. Once again, I express my sincere thanks to Professor Lizzie Kurian John and her husband, Dr. Professor Eugene Brito John. Both of them were my juniors. I am so proud to say that both of them were my juniors at College of Engineering, Trivandrum. Once again, on behalf of the entire Amarjyoti family who gathered here, I express my heartfelt gratitude to Professor Lizzie John Kurian. Thank you.
Thank you, ma'am. That was truly insightful. Now, as a token of our gratitude and appreciation, I now respectfully invite Reverend Father Roy Parevaramil, Director of Amarjyoti College of Engineering, to kindly come forward and present a memento to our esteemed guest, Professor Lizzie Kurian John, in recognition to her valuable presence and inspiring session with us today. Now, to formally conclude our session, I would like to invite THG for the vote of thanks.
On behalf of Amarjyoti College of Engineering, it is a privilege to extend our gratitude to our distinguished guest, Professor Lizzie Kurian John, in Department of Electrical and Computer Engineering from the University of Texas, for today's inspiring session on for ML and with ML, the new normal in system design. Thank you, ma'am, for sharing your experiences and giving us a glimpse into your journey. Your insights in machine learning and the integration of AI has given us a clearer vision on where our whose work bridges rigorous research with real-world impact. A sincere thanks to Reverend Father Bobby Alex, our manager, and Father Roy Parambil, director, and to the management and college leadership for continuously creating opportunities that bring world-class academia to our campus. A sincere thank you to our principal Lilikuti Jacob for envisioning and supporting this distinguished lecture series. Dean Research, Dr. Sony C. George, for organizing such an amazing session. Gratitude is also due to the coordinators of the Silver Jubilee Celebration, the organizing committee, the technical team, and everyone who has worked behind the scenes to make this event seamless. A special thanks to our faculty members and to the students for your attentive listening. Thank you and have a wonderful day ahead.
And with that, we have come to the end of today's session. Thank you all for your gracious presence. That was truly insightful. Thank you.